All right, friends, welcome to class. Can you all hear me if I don't use a microphone? Is it okay? You can still hear? Fine? All right. Welcome to 285. You're taking this in the spring. What are you, nuts? Is my question. So, no, actually, this is going to be a really, really fun semester. I actually haven't taught this class before. Been teaching at BYU since 2011. I've taught OChem that whole time. Never taught this class that's sort of OChem and biochem to this audience. So many of you are hoping to join the nursing program. Some of you there, yes? What other majors or reasons are you taking this class? Go ahead. Dietetics, nutrition, dietetics, food science. Go ahead. Go ahead, what? Sorry? Athletic training, yeah. Medical lab science, okay. Anybody else? Anything we haven't covered? I think for most of you, this may be the last chemistry class you're going to take. So that's yay. What it means is that nobody in your future is depending on me to teach you any particular chemical thing. So my goal, or rather, they want you to know some basics of organic and biochemistry. My goal is to give you the tools that you need to understand the world around you at the molecular level. And as we explore the structures and processes of living systems, starting very, very small with molecules, I hope that you'll learn, as we do at BYU, your dual heritage of learning by study and by faith. I hope that the chemical principles you learn will give you a sense of inspiration and wonder, awe at the great Creator and His creation. And so in this class, you're going to learn to describe and predict molecular behavior based on structure. You'll learn how to explain biomolecular structure and function, understand the relationship between structure and function. We'll talk at the end about how major classes of drug molecules work, what their targets are, what their structures are, how they influence things. Along the way, even though this is a science class, I hope you'll develop intellectual and spiritual virtues. Most importantly, curiosity, creativity, perseverance, a little bit of humility. That may happen whether or not you want, and that's okay. And a continuing desire to learn throughout your life. How the class is going to work, I've got the syllabus. It's laid out in pretty good detail. I'll draw your attention to a few things. First, we are not using a textbook. Many of you may have access to your Chem 100 or 101, I can't remember what the name of the class was, textbook. That also has a section on organic and biomolecular chemistry. If you need a reference and you need someplace to go, you can certainly refer to that, but I'm not going to be assigning reading or problems out of that textbook. The reason is it does not cover the things I want to cover so you can understand the world around you at the molecular level. If anything, you are more capable than that textbook gives you credit for. So that means that you're not going to have the crutch of a textbook to look at. How are you going to prepare for class? Well, I don't use a chalkboard. I use an iPad and an Apple Pencil, and I project it up there. We can zoom in, we can zoom out, we can scroll back, we can copy, we can paste, and I will post those notes on the content page of Learning Suite. I also record lecture, and I post that. Now, I have seen how this has played out ever since COVID. Everybody swears up and down that they attend class, but I look out at the audience, and in a class of 250 students, there's more than 100 seats empty because when a lecture is available online, I know the natural individual, the natural human is an enemy to God. And so we tend to think, okay, if I can just watch this in my jammies, then what's the point? That would be a mistake for a couple of reasons. First, there's a reason that the church, after COVID, you guys lived through that, right? Do you remember how we had individual sacrament meetings in our apartments and homes? Do you remember why we stopped doing that? In part, it was because there's strength in gathering together and learning together. There's connection as we interact with other humans. I don't want you to miss that. The second thing is this class isn't going to be just lecturing. We can't sit for 2 hours and have me talk at you. So each class, there's going to be a quiz. Now, I've already handed you your first quiz. You're not expected to be able to do this when you get to class. As we go through class, I will pause and then say, okay, now do problem 1. You'll do it. Then we'll go through the answer. You'll grade it yourself. And at the end of class, you'll turn it in up front. One of the TAs will record it. You're going to get 5 points just for completing it. Okay? So this is low stakes. Make mistakes, fail early, fail often, see what you're supposed to get out of a lecture, make a mistake, figure out how to fix it. This is your first pass about what do I need to learn today, all right? And we'll talk about it. We'll ask you to talk to your neighbor and try to figure out what you did wrong, come up with suggestions for improving. If you're not here, you can't do it. There will be one of these basically every class period. 30 of them are going to count. So however many we get done, we'll drop 3 or 4. If you're not here that day, if you have to leave, if you're late or whatever, if you're not able to complete it, it'll just be one of your dropped grades. But there's really no, I want to do the video option, can I just do the quiz from home? No, because part of the learning experience is being here. That's going to be about 15% of your final grade, which you're going to get just for showing up. Yes?
So for those 3, if we make it to all the classes, would that add towards our grade in help or?
If you make it to all the classes, does it add? No, you can afford to drop 4. I mean, I suppose we could work something like that in, but I have another extra credit opportunity, which I think will be more meaningful. Okay, so that's 15%. Need to see the math. Another about 25.5% is going to come from a weekly problem set. Your first one is here. It's assigned today. It is due Monday, May 5th, at the beginning of class right here. And this is going to be related to your quiz problems. If you look at quiz 1, and then you look at some of the problems on the problem set, they will line up, only the problem set will push you harder and longer, okay? You're going to do this, and you'll turn it in. The TAs will grade it. They're going to grade most of it on completion basis, but there will be a few questions, 1 or 2 out of the 10, 5 to 10 questions on the problem set that they'll grade on a 2, 0, 1 scale. 2 is pretty good, 1 is about halfway there, 0 is not enough. Then they'll turn it back to you sometime that week, probably Tuesday or Wednesday. You can look at the problems that they graded. If you got them wrong, you have a chance to submit a correction for full credit, okay? And that's another chance for you to examine, what am I getting wrong, what am I missing, what do I need to work on? I will propose for those problems that they grade, I'll propose some alternative problems. The syllabus explains how you're going to do this. You get a problem wrong, you write the correct answer, you explain your misunderstanding in 1 or 2 sentences, and then you try a similar problem, a similar second problem that I will provide for you. You submit that to the TA, and then they can give you full credit, okay? The TAs will be recording this on Learning Suite. I haven't got the Learning Suite thing live yet, but eventually there'll be 30 slots for quizzes, 7 slots for problem sets. Overall, if you add up the quizzes and the problem sets, there's 7 problem sets, 15 points per problem set. Quizzes and problem sets overall are going to account for about 1/4 of your grade, which if you show up and do the work is like getting 100% on a 250-point midterm. So that's going to be a reward for doing the work, but it's low stakes. You just show up and you do the work. Along the way, though, you got to pay attention to what you're doing wrong and figure out how to get help on those skills. How do you get help on those skills? You ask questions in class, you visit the TAs, you talk to me in my office hours, which are going to be Tuesdays and Thursdays right after this class until 4. Sometime later today, take a look at the second page of the syllabus, which is my 9-step program for success in 285. Some specific things you ought to be thinking about. This is the advice that I give people after they take a midterm exam and don't do very well on it. So if you want to look at that advice earlier and take it earlier, it could make a difference. Let's talk about performance. So as I said, about 25% of your score is going to be based on preparation, just doing the work. The remaining 75%-ish is going to be midterms. 3 midterm exams scheduled on the last page of the syllabus. It's a whirlwind. It's every couple of weeks. So we got one coming up. and then a final exam. The midterms are each worth 15% of your overall grade, 150 points each. The final exam is worth almost twice that, 295 points. Now, I know that makes some of you nervous because high stakes for the final, but you have a lot of time to get there. And the other thing is I will also allow you to replace your lowest midterm score out of 150 points with whatever percentage you got on the final. So if you struggle on the first midterm and you're like, oh no, don't worry, because if you improve by the end of the semester, you can not only get the credit on the final exam, but you can actually get your final exam score replacing one of your midterms. There's a lot of other ways to structure this. That's what I'm trying this semester, okay? Lastly, there will be an extra credit option, and it's totally optional. You don't have to do it, but you might want to. So the American Chemical Society has prepared a standardized national statistically normed test for this class. It's called the General Organic and Biochemistry Test, although we would only do the organic and biochemistry version. Some of you may have taken the general version at the end of Chem 101. And this is a way to just see how we're doing relative to the rest of the nation. I kind of like those data. It helps me figure out how I'm teaching and provide evidence to other people about how teaching is going. On the other hand, I'm not teaching to that test, and frankly, you're going to learn a lot of stuff that isn't on the test that's crucially important. So I don't want it to count hugely for your grade, but I want you to care about it. So you get 5 points extra credit for thoughtfully taking the exam. You can get up to an additional 10 points ranked to your percentile score on that exam. So if you finish in the 100th percentile, you get 10 points, 15 points overall. At the end, that's 1.5% of your grade, and at some places that will be enough to move you up to a higher grade bracket. So at the end of the semester, everybody's, is there anything I can do? This is the thing you can do. All right, well, it'll be at a time and location to be scheduled. It'll have to be outside of class. We'll make some, because of that, we'll make some accommodation for people that can't make the scheduled time. It is a timed test. More details will come later. Just want you to try it, see what happens. Very, very low stakes, and it can only help you. That being said, you don't want to do it, totally fine. Okay, grade scale, just look at that. The posted grade cutoffs are a starting point. They will never be higher than listed there. Usually the cutoffs in the B to A range are about close to what they are listed in the syllabus. Usually the cutoffs in the C range are somewhat lower than listed in the syllabus. So sometimes the cutoff between C minus and D is in the low 60s. So if you get a 67 or a 68 on a midterm exam, you should not be thinking, oh my goodness, I failed, or even, oh my goodness, I got a D. You should be thinking, that's probably in the C to C minus range. I definitely want to do better, but all is not lost. Okay, got that? Usually the cutoff between D and E is around 40%. And if you do the work, you should be well on your way to getting better than that. All right. Any questions about the structure of the class? Trying something new this time, which I don't typically do. Some of my colleagues have said, and I've learned from them, that basically my job is to teach you organic chemistry. Though I feel like at BYU, President Kimball in his second century address talked about keeping everything we do bathed in the light and color of the gospel. So I'm trying something new. With each problem set, there's going to be an optional reflection question at the end. This is related to that developing spiritual and intellectual virtues outcome that I've got on the first page of the syllabus. This is optional. You don't have to do it. I don't believe in grading your testimony, but you can do assessments without grading. And so if you want to do this, it's not worth any points, but if you want to, you can reflect on how what we've learned this week has influenced the way you think about things from a spiritual perspective. We won't read the prompt here. You can look at it. And I may invite over time, if some of you have thoughts, to share on Mondays as you've had a chance to reflect. For me, the kind of things that I think about at the beginning of this class come from Psalm 19, where in the first verse the psalmist says, "The heavens declare the glory of God, and the firmament showeth his handiwork." Or from the Book of Mormon, Alma chapter 30, verse whatever it was, 44. All things denote there is a God, yea, even the earth, and all things that are upon the face of it, its motion, and all the planets which move in their regular form do witness that there is a supreme creator. That's about big things out there. This class is about small things in here. We're going to be talking about the atoms and the molecules and the systems, but I hope you'll be filled with just as much wonder and curiosity about that as you might be as you look up at the stars, because the scale is just as vast and bewildering. All right, any other questions about how things are going to go? Yeah.
So, for some of us, aka me, it's been a while since I've taken Chem 101. What do you suggest is like a nice review?
For some of you, it's been a while since you've taken Chem 101. What do you suggest for a nice review? I would say relax, because basically everything you're going to need to know, we're going to talk about. So if you know that we're not going to do a lot of math. The basic math is going to be, can you count? And is this number bigger than that number? And I think that's it for the math. I'm trying to think what else. So yeah, we'll start at the beginning. We'll go from there. Principles you learned in Gen Chem, if you remember the concept of electronegativity, that's useful. We'll talk about that too. So I think you can relax a little bit there. Don't stress out about that. I think you'll be fine. Other questions? Are you ready? Okay. I'm kind of a Star Wars nerd, so I feel like this moment is where Luke, some of you may not know Star Wars references. It's okay, you'll get used to them. But when Luke shows up on Dagobah and he finally discovers that the little green man is Yoda, he says, "I'm not afraid." And Yoda says, "Oh, you will be." Right? That's sort of how I feel. You're sort of Luke and I'm sort of Yoda telling you to be afraid. Go ahead.
On these practice problems, or the problem sets that are due on Monday, is that something that we are allowed to work in groups?
Yeah, by all means you can work in groups. Understand though you won't be taking the exam in groups. So help each other, work in groups. If you need help from a TA, please ask, or for me, please ask, but don't. The quick and easy path to the dark side will be to ask the TA or me to just walk you through it and do it for you. You're going to have to resist that temptation because that will limit your growth opportunities. But yeah, by all means, work in groups. Yes?
Will these be like reposted in Learning Suite so we can view them again without our work on them?
Yeah, so I will post the problem sets and the quizzes in Learning Suite. I'll also post the keys. I'm not sure if I'll post the key right away on the problem set or give you a chance to rework it once you know you got it wrong. But I'll eventually, so I got to figure that out, but I'll eventually post the keys so you can do all of that. Yeah? How can you figure out TAs? TAs, are you here today? Did I meet you yet? Yes, okay. Please stand up and say hello to everybody.
Hi, I'm Maggie. I'll figure out my hours soon. So
What we'll do is we'll post them on Learning Suite.
yeah.
And
I'm Myler.
say that again? Myler.
with an M.
Okay, but not like the balloon. Mylar. No, don't call him Mylar. E, okay, good. All right, Maggie and Myler, how long has it been since you took the class?
I took it fall.
Okay. And Myler, how about you?
So they assigned me, I've taken biochem and all that stuff. I haven't taken this class.
You've taken 481 and 351? Okay. They're both experts. Maggie, did you take it from Paul Savage?
Yeah.
Okay, so I'm going to sort of be following his way of thinking about things, homo, lumo, but yeah. We'll talk after class a little bit about what I'm going to need. Okay, other questions? All right, now that I've told you to be afraid, sorry, that's not the right message. Fear not, right? Let's have a prayer to begin. Would anyone like to offer a prayer? I won't make eye contact. Go ahead. Yes, thank you. Amen. Thank you. How's the lighting? Can you guys see that screen or do we need to change it? Not that. That's terrible. Probably not that. Is that okay?
Yeah.
Anyway, all right. So, to begin with, we need to talk about the most important, well, the simplest organic molecule in the universe, and talk about something that is called the covalent bond. So here is the simplest organic molecule in the universe, hydrogen, or H2. What I've drawn for you there is called a Lewis structure. You may have seen it before in your general chemistry textbook as that. What have you heard about a covalent bond before? Go ahead.
They share the electrons, the valence electrons.
Okay, two elements sharing the valence electrons. Good. What else?
Pretty strong.
Pretty strong. Okay. We could actually measure how strong a covalent bond is by how much energy you have to add to cause it to break. When that happens, breaking the bond, there are multiple ways to break a bond, but one of the easiest to understand is where either atom takes an electron with it. Okay? What else have you heard about a covalent bond? Yeah, go ahead.
Does it, okay, I actually can't remember if it's between two nonmetals or metal and nonmetal, but I know maybe sometimes it asks the property of the elements.
Okay. Yeah, so covalent sort of just tells you that it's about valence electrons, and co means together, so it's sharing of valence electrons. You probably learned about something called an ionic bond in general chemistry, where there's a large difference in electronegativity, and where they don't share electrons, one actually has all of them and the other doesn't, or some such thing. Put a pin in the idea of ionic bond. In a week or so, we're going to show you that ionic bonds aren't real. We just hold on to that thought. Just come back to it. But covalent bonds, yes, involve sharing of electrons between two elements. And generally in this class, we're going to be talking about hydrogen and carbon, nitrogen, oxygen, phosphorus and sulfur, and some of the halides like chloride. Okay? So we're going to be dealing with things that are pretty close in electronegativity to each other, such that we're not going to be dealing with, so that we'll always be talking about electrons being shared. All right. Let's talk about how covalent bonds form, because you can memorize that, they like to share electrons so that they can achieve what? Do you remember what they're trying to achieve? Go ahead.
They just want to be stable with all 8 valence.
Right, they want to be stable with all 8 valence electrons for something that's in the second row of the periodic table, or if it's in the first, 2, right? But who made up the octet rule or the 2 electron rule for the first row? How can you understand that, and why do bonds form in the first place? The answer is bonds allow electrons to be lower in energy than they would be if they are not in bonds. And that's an important principle. Bonding is favorable or stabilizing. Electrons that are in bonds are lower in energy or more stable than what we might call non-bonding electrons. So in this reaction that I drew, where we break the bond to go from a hydrogen molecule to 2 hydrogen atoms, that's uphill in energy. That's unfavorable. Let's talk a little bit more about how that happens. Did you guys learn in general chemistry about orbitals? A little bit. What is an orbital? Go ahead.
It's like an area where electrons are likely to be.
An area where electrons are likely to be. Good. Others? Is it the electron taking a circular path or an elliptical path around the nucleus like we see in planets? No. I mean, that was how people used to think of it. The orbital is really what we're going to call a wave function. And the wave function describes the wave-like properties of an electron. This is an important thing from quantum chemistry. Electrons have particle and wave-like properties. You can shoot them at stuff and they can bounce off stuff as though they were particles, but you can also shoot it at a diffraction grating and it will make a pattern as though it were a wave passing through that diffraction grating. Something that's difficult to understand, but in this class we'll think of electrons as having wave-like properties. So let's think about waves. You can think about sound waves, you could think about waves on a string, you could think about waves in a pipe organ. Any of you have experience with a guitar or a stringed instrument? Okay, a little bit, all right. So in a stringed instrument, the string is fixed at two ends. And then if you pluck the string, there are certain vibrational patterns that are allowed. Others just don't work. So for example, if you pluck this string, one of the allowed vibrational patterns is a wave that looks like this, and it's going to oscillate from one side to the other with time. That's not a good drawing, but you have to imagine, right? That's one allowed waveform or wave function or energy level. Another allowed wave function or waveform or energy level is this wave. And it starts here, and then I guess I should have chosen red for that color. Boom, this is why I love the iPad. And then as time increases, the wave will move and adopt this form, and it's going to oscillate between those two. Both of these are called standing waves. And this is really interesting. Standing waves are the only waves that can exist for that string that's fixed between those 2 points. And though the wave itself can oscillate, some characteristic positions stay the same. For example, in this lowest energy wave, the maximum, which I've drawn poorly, is right in the middle, right in between the two. And even as the wave's going up and down, the position of that maximum or that minimum in amplitude stays the same. Notice that for the next higher energy wave, the positions of the maximums or minimums stay the same, but there's also this point in the middle, which is called a node, that always stays at 0. Notice that the wave, if I draw some kind of y-axis here that describes what we might call amplitude, notice that at any given point in time, the wave can have positive amplitude or negative amplitude. And there are places where the wave goes through 0, right? This is called a standing wave. A couple interesting properties about waves. This standing wave that has one node has a higher frequency than the one that has 0 nodes. This is 0 nodes, this is 1 node. The one that has 1 node has a higher frequency and therefore a higher sound. Another interesting feature of waves is they occupy all the space between the two ends of the string. You could ask, where is the wave? And the answer is, the wave is on the string everywhere the string is. So it doesn't make any sense to ask where on the string is the wave. The string is the wave and it occupies all the space in the wave. If you happen to have access to a guitar, you can test this hypothesis. When you pluck a string, both of these waveforms coexist on the same string. They exist in the same space. They're at different energy levels, so that's fine. If you pluck the string, the most dominant note you hear is this one from what's called the first harmonic, or the wave that just oscillates up and down on either end. Yeah?
Does that have to do with like a guitar where you have the smaller strings and like the higher sound?
So with the guitar, yeah, if you have smaller strings, you get a higher sound, and I don't actually know the physics there. I do think that in the case of the guitar, if you increase the tension on the string, it changes the pitch of the sound. Another way to change pitch would be to change the length of the string. Of course, that would be inconvenient for a guitar because we don't have arms that are long enough, right? So they do use the weight of the string and the tension to adjust pitch, and that's where our analogy is going to break down. But if you pluck a string on a guitar, you're going to hear the first harmonic, which is this lowest energy waveform. But there should be simultaneously on that string this waveform, which is going to have a node in the middle, a place where the wave goes through 0. So you can do this test. You can touch the string in the middle. If you want to know where that is, that's the little dot on the 12th fret. If you tap the string there, you're going to suppress this waveform, but this one will still survive. It doesn't get damaged because you're tapping it where it already goes to 0. That's one way to demonstrate to yourself. That's neither here nor there. I'm not going to ask a question on the exam about what happens if you tap the 12th fret of a guitar. Or I guess it could. Now you'd be prepared for it. But the idea is that the wave exists when the wave passes through the node, it exists on either side of that node. You can touch the string at that node and it doesn't do anything. You'll actually hear this with your ear. When you touch the 12th fret, the note you hear will go up by 1 octave. That's because you're no longer hearing the first harmonic, you're hearing the second. Kind of cool. All right. Electrons have many of these same properties. Electrons aren't constrained by 2 ends of a string, but they are constrained by a nucleus. The electron, which is negatively charged, is attracted to a positively charged nucleus. And if you allow the electron to act as a wave around that nucleus and you solve the equations, you get waveforms for an electron that are pretty similar to these waveforms, okay? So let's talk about waveforms or orbitals for electrons near a nucleus. So for hydrogen, the orbital is called the 1s orbital. Why it's named that doesn't matter. You heard of the 1s orbital before? What's its shape look like? Do you know? It's a sphere, okay? So here's the hydrogen nucleus, and the 1s orbital is a sphere. Now, if you look at this lowest harmonic wave that we did for the string, the wave doesn't change signs. The lowest energy wave doesn't change signs from one end to the other. Similarly, in the hydrogen lowest energy waveform, the wave doesn't change its sign anywhere, meaning it's all either positive or negative. Now, when we talk about waves with electrons, we have to be real careful when we talk about the amplitude or the magnitude of a wave. It can be positive at a certain time, or it could be negative at a certain time. But we don't want to get confused with charge. So when we draw orbitals or waveforms for atoms, we're going to use color or shading to indicate areas of the wave that have the same sign. Okay? So for the 1s orbital, I'm going to use the color orange, indicating that the wave that the electron is all the same sign. Could be positive at one point, could be negative at another point, but at any given instant, it's always the same sign. In the same way that at any given point in time, the magnitude of this lowest harmonic wave is all the same sign. Does that make sense? Sort of, a little bit? Okay. So, with the idea of the 1s orbital, you're now ready to think about bonding in hydrogen. When we think about bonding in organic chemistry, to make a bond, we are going to mix the atomic orbitals, that is, the individual orbitals that are on each atom, to make a molecular orbital. What do I mean by that? Imagine that we take 2 hydrogen atoms, each of them having this 1s orbital structure, and I bring them together and they're going to approach each other. At this point, we're just going to think about the orbitals. As these orbitals approach each other, they're going to start to overlap with each other, right? Now here's an important concept from waves that applies to orbitals. And that's the concept of constructive interference. If I have two waves and I add them together, they can either reinforce each other or destroy each other. Let me give you an example of how this might occur. For example, imagine I take this waveform here, where the wave is all positive. This is our oscillating string. And imagine I add to it a second wave in the same place, also oscillating at the same speed and with the same sign. When I add them together like this, what do I get out? Bigger wave, right? The amplitudes simply add. It's just addition. They add like this, and the wave that I get is more positive, right? The second concept is that of destructive interference. So if I add two waves together and they have opposite sign, that is, if I add this first harmonic wave that we were talking about, and then I add this one, and their opposite sign, we'll use the color pink for the opposite sign. What do I get when I add them together with exactly the same magnitude but opposite sign? Nothing. Destructive interference. They cancel each other out. Okay? This is important because when we make a bond, when we mix the atomic orbitals together on each atom to make a molecular orbital, we have to consider two options. First, constructive interference, where we bring the two atoms together and their waveforms have the same sign. And second, destructive interference, where we bring the two atoms together and they have opposite wave function sign. So to show this, let's imagine this one is, say, pink means negative magnitude, orange means positive magnitude. I bring the two hydrogen atoms together. Where they overlap, what's going to happen? The positive sign on one side and the negative sign on the other side going to cancel each other out, go to zero, right? So I'll show you the results of adding together two wave functions constructively, or what we might call in phase. The resulting orbital that we get out looks like this. It has most of the wave is between the two atoms, and we call this a bonding orbital, because if I were to put electrons in that orbital, they would tend to spend most of their time between the two atoms. The out of phase or destructive interference option, where the two orbitals come together, they cancel each other out. I'm going to use a black dotted line to indicate the place where the wave forms have canceled each other out and where the wave has, as a result, gone to zero. So between the two nuclei, as they approach each other, the orbitals cancel each other out and go to zero. I'm going to use this symbol, the Greek letter psi, as a representation of the wave function. And psi equals zero at that location. That is a node. Okay? So when I bring two orbitals together for two atoms, I mix them together to make a bonding orbital where they reinforce each other constructively, and then I make this second orbital where there's a node in the middle. We call this one an antibonding orbital. And I want you to see the analogy between what we drew here for this bonding orbital and here for this antibonding orbital. Notice that the bonding orbital is like this one. It has all the same sign from one side of the molecule to the other. The antibonding orbital is like this one. It has positive sign on one side and negative sign on the other, with a node in the middle, or a place where the orbital goes to 0. Okay? The main conclusion is that for each covalent bond in an organic molecule, you have a bonding orbital that is lower in energy than the atomic orbitals that you started with. This bonding orbital is lower in energy than the 1s orbital. And you have an antibonding orbital that is higher in energy than the 1s orbital that you started with. Why is the bonding orbital lower in energy? Well, electrons in that bonding orbital get to spend their time between two nuclei, and they're attracted to those two nuclei. The other explanation is that electrons in the bonding orbital get to spread out more, and spreading out electron density through space is always stabilizing. In contrast, the electrons in the bonding orbital spend most of their time away from the space between the two nuclei, so they don't experience the nuclei as much, so they're higher in energy, and also they're, well, there's another explanation from quantum chemistry that we won't really talk about. But for each bond in an organic molecule, you need to be thinking, okay, there's a bonding orbital and an antibonding orbital. For hydrogen, if we were to plot out in energy where these orbitals show up, if this axis means energy, higher energy, lower energy, and if this starting point is the energy of a non-bonded 1s orbital, just on an isolated, man, penmanship is a struggle here, energy of a non-bonded 1s orbital on hydrogen, then the bonding orbital that we just made, which looks like this, is going to be below that dotted line. And the antibonding orbital that we just made is going to be above that line by about the same amount. And I guess I need to shrink things, don't I? Oh well. Now, if you look at hydrogen, and we draw it like this, or we draw it like this, how many electrons are involved in the bond? 2. So in my energy diagram, where should those electrons go? You should always fill the lowest energy orbital first, and the lowest energy orbital can take 2 electrons, right? As long as they have opposite spin. We won't worry about spin of electrons in this class, but when I draw an electron pair in an orbital, I'm going to draw it like that. The one up arrow and the down arrow just remind you that they have opposite spin. If I don't do that, my conscience is going to drive me nuts, so I sort of have to, but you won't really need to worry about that. You take the available electrons and you fill up the bonding orbital, and notice in a stable covalent bond, the bonding orbital is filled, the antibonding orbital is empty, okay? Each covalent bond in an organic molecule has a filled bonding orbital and an empty antibonding orbital. Now here's the exciting part. Remember when I asked you who made the rule that you can only have 2 electrons for a first row element? You can derive that rule now with this energy diagram. Tell me what would happen if we change the atoms from hydrogen to helium. Helium has the same 1s orbitals that hydrogen does. How many valence electrons does helium have? 2. So change the picture. What if this is helium? What happens? How many valence electrons, if I were to invent helium-2 and ask you, is that a stable molecule? How many valence electrons does helium have? It has 2. So we would have how many total? 4. So for helium-2, what happens? Fill the antibonding orbital, that fully cancels out the benefit of bonding. If you fill the antibonding orbital, you cancel out the benefit of bonding, and the bond breaks. So helium isn't trying to follow some abstract rule. Helium doesn't bond because when the two helium atoms get close to each other, there's no benefit to bonding. Okay? Questions about that? That's a really important foundational principle for this class. You will see anytime we fill an antibonding orbital, a bond breaks. And we're going to use that a ton of times to describe why and how chemical reactions happen. Yes?
Is an anti-bonding orbital always going to be one that doesn't have a full valence shell? Or
So an antibonding orbital will always be empty in a stable molecule. In molecules that have a full valence shell, the antibonding orbitals are empty. Yeah. Others? Yeah.
I'm sorry, could you briefly review again what you're trying to show by hydrogen in yellow, hydrogen in pink?
Yeah, hydrogen in yellow and hydrogen in pink. This means opposite magnitude or amplitude, however you want to think about it, opposite magnitude or amplitude of the electron wave, which is the orbital. No, so spin is not related to the sign of the orbital.
So, in theory, we're just gonna, like, if we have a question similar to this one, you'll always tell us, hey, this one has negative, this one has positive.
Right, you will use the color to indicate parts of the wave function or orbital that have opposite sign. And it doesn't matter that one's positive or negative versus the other way, it's just that they're opposite each other. Yeah. Okay? Yes?
Bonding and anti-bonding orbitals always mirror each other, so like if there's like there'd be four antibonding.
That's right. So bonding and antibonding orbitals will always mirror each other. If you have 4 bonding orbitals, you'll have 4 antibonding orbitals. Okay. So now we need to get just a little bit more complicated. Let's do something like methane, which is CH4. What orbitals are available to carbon? What are the valence orbitals for carbon? Do you remember? There's 4 of them. One of them is called 2s, and then the others are called 2px, 2py, and 2pz. Does that sound familiar? No. Okay, you're learning it for the first time. That's okay. We're going to talk about the shapes of these orbitals. The 2s orbital shape is also a sphere. Now, it's a little bit more complicated than that. You don't need to worry about this, but inside that 2s sphere, there is a smaller sphere that has opposite wave function sign. You'll see that the orbitals that come from the second row of the periodic table all have one node. That is one place where the sign of the wave function changes. I'm going to just pretend we didn't talk about that because it doesn't matter for any particular purpose. All right? That's the 2s orbital. It has the same spherical shape as the 1s orbital. It's just a little bit bigger. Then there are p orbitals, and these are named x, y, and z because they are aligned all 90 degrees away from each other. We might call this x, this one y, and this one z. You guys know how to think in 3D-ish? If you don't, we'll help you. Class is going to push you on this. So the p orbitals are a little bit higher than the s orbital. The 2p orbital looks like this. I'm going to use a dot for the center of the carbon nucleus. The 2p orbital has this sort of clownish bow tie shape. Some people call it a dumbbell, but it doesn't look like a dumbbell. It looks like a propeller or something. On one side, it has one particular sign. At the nucleus, there is a node. And then on the other side, it has opposite wave function sign. So that's the 2px orbital. It's oriented along the x-axis. Please don't misunderstand, the 2p orbital is not an electron hopping around from one side to the other, back and forth, back and forth. Instead, there we go. Instead, the electron simultaneously occupies both sides of the node in the same way that the string occupied both sides of the 0 point. Okay? The electron is in both places simultaneously. Right? All right, so the 2py orbital, or rather, let's do the z orbital next. The 2pz orbital is like this. Its node, it's aligned along the z-axis, and its node is here in the xy plane. And then lastly, the 2py orbital is difficult to draw. It's sort of pointing out at you and going back away from you, aligned along that y-axis. Okay? So carbon has those 4 orbitals, a spherical one, and then these dumbbell or propeller-shaped ones that are oriented each 90 degrees away from each other. So the 2p orbital, the 2px orbital points in this direction, 90 degrees away. The 2pz orbital points in this direction. And then 90 degrees away from that, the 2py orbital points in this direction. Up, down, left, right, front, back. 3 dimensions. Yes?
Wait, so is there a node in the 2py?
Yes, there is also a node in the 2py. We could draw it like this. It's the it's the xz plane. Okay, now, here's the problem. Oh, and we'll just say that hydrogen just has a 1s orbital. If you look at methane, you might draw its Lewis structure like this, and that is fine. But valence shell electron pair repulsion tells you that the bonds, the electrons in the bonds in methane want to get as far apart as possible, so that methane adopts a tetrahedral geometry. Tetrahedral geometry means the hydrogens, the carbon-hydrogen bonds in methane, are all about 109 degrees away from each other. That's what a tetrahedron is. Does that sound familiar? Have you heard of tetrahedral geometry before? Okay. Now you can see the conundrum we're in. When we made a bond in hydrogen, we just took these 2 spheres side by side and we put them close together. And if you are trying to think about how might I make the bonds in methane from the orbitals on carbon that are available to me, you might say, okay, let's take one of those 2p orbitals, say the 2pz orbital, and let's just take a 1s orbital from hydrogen and stick it on the end of it like this. Okay? To draw that out, what would that look like? Well, here's the 2pz orbital. Here's a hydrogen. Let's go ahead and take the hydrogen and have it line up with and overlap with that 2pz orbital. Okay, looks all right. What if I do that for the other 2? What would the bond angles be? What are the angles between the p orbitals? 90. So if I use those p orbitals to make bonds with hydrogen, I get the wrong answer for bond angles. So chemists invented a new way of thinking about orbitals, and that is called hybridization. Have you heard of orbital hybridization before? Some of you maybe yes, some of you maybe no. I think this is maybe new. It may not be covered in any detail. The idea of hybridization is that before attempting to make a bond, we first consider the molecular geometry about an atom. In this case, for methane, the geometry we concluded it had to be was tetrahedral. And then we're going to mix the atomic orbitals together on carbon to get hybridized orbitals, and they're going to have altered shape and orientation. By that I mean where they point in space. So for a carbon in methane, we're going to say that that carbon is sp3 hybridized. And what sp3 hybridization means, literally, is that you add the 2s orbital together with the 2px and the 2py and the 2pz. You add them all together and you get 4 new sp3 hybridized orbitals out. And how do you do this? Well, you don't ever have to do that. That is the maths of molecular orbital theory, which we're never going to hold you responsible for. But when you do this, what you get out is a list of 4 sp3 hybridized orbitals. One of them looks like this. An sp3 orbital looks like a distorted p orbital. It has one side, so this is a propeller that would cause a plane to absolutely fall apart. It has one side that's much larger than the other side. Okay? And there are 4 of these, and they're each oriented 180 degrees away from each other. So an sp3 hybridized carbon looks like this. Here is the carbon. One of those sp3 orbitals is oriented here. There's a node at the carbon. The large lobe has, we'll call orange wave function sign, and the smaller lobe is pink. And then there's another one oriented in this direction. Another oriented in this direction with a smaller lobe on the other side. And then another one over here, and we're struggling to get the geometry right in this 2D drawing. What you have to understand is that the large lobes on each of these sp3 orbitals are 109 degrees away from each other. So by hybridization, we solve the orbital directionality problem. We can now make each of the carbon-carbon bonds in methane by combining one of the sp3 orbitals on methane with the 1s orbital on hydrogen. In other words, if I want to make a model of bonding in methane, all I have to do is bring a hydrogen atom and have it overlap with the large lobe of the sp3 orbital on carbon. And I do this 4 times, and I get 4 new bonds between carbon and hydrogen. And they're all oriented in the exactly correct direction that's predicted by our understanding of molecules. Okay? Each of those bonds in methane that comes from overlap of an sp3 orbital with an s orbital, we're going to call a sigma bond. And that term sigma bond was, that's the Greek letter sigma. We've been talking about sigma bonds for years, long before your generation was talking about so-called sigma males, whatever that means. My son has tried to explain this to me, and I'm like, I just don't understand it. I do know what Riz is, though. Talk about Riz. And from my teacher's quorum, I learned what it means to be finna crash out. So I hope that all of you are not at that stage yet. Okay, that's a good time to take a break. Let's take 5 minutes, and then we got to go.